Hello, and welcome to Backer Breaks It Down. In this episode, we are going to analyze and calculate with the number E. Okay, so the number E is known as like the natural base, and it's approximately 2.71828. And it says below that E is the base rate of growth shared by all continually growing processes. E lets you take a simple growth rate where all change happens at the end of the year and find the impact of compound continuous growth where every nanosecond you are growing just a little bit. So the natural base E basically tells us what's happening at any given moment. Okay. And so when we were studying compound interest, we talked about how interest could be compounded quarterly, monthly, you know. So over here, N is representing the number of compounding periods. And then the right-hand column is representing the 1 plus R over N to the nth power. So for one compounding period, you get 2. For 2, you get 2.25. And notice what's happening to the x values over here. They're getting pretty big pretty fast, but they are definitely increasing pretty quickly. But look at these y values. These y values are starting to level off. And where are they leveling off? At E, at approximately 2.71828 ... It's kind of like pi, okay? So now we have exponential functions that I like to call the non-continuous. Those are the base B's that we've been working with. Now we have these continuous exponential functions. Notice that the base of the continuous exponential function isn't just E, it's e to the k power, okay? Now k is going to be positive if we're talking growth, and it's going to be negative if we're talking decay. So notice the rule says k is positive R or k is negative R. R is your percent rate. So turn that percent rate into a decimal, and then it's going to be in the exponent and positive for growth, and in the exponent and negative for decay. Now, if I know what k is, if I know that numerical part of my exponent, I simply multiply it by 100%. That's how I'm going to turn it into a percentage. I can calculate compound interest if it's compounding continuously. I said that weird. I'm using this formula, B equals P times e to the RT power. B is your balance, P is the principal, R is the rate, and T is the time. And then, of course, there's an APY formula for the effective rate. Okay, so let's take a look at this function here. We have the quantity Q equals 0.01 times e to the negative 0.2t power. I want to know a few things about this function. First off, what is the quantity at the time t equals 0? Right? Well, this is your initial value, and the initial value is still that coefficient. So in this case, 0.01 is the value when t is equal to 0. Now, in order to answer part B, is the quantity increasing or decreasing over time? I first want to draw your attention to part D. It says, is the rate continuous? Okay. Well, since the function is base E, then yes, it is continuous. Okay, so anytime you see that base E, it is a continuous function. So now back to the question, is it increasing or decreasing over time? Well, going back to this table here, it's increasing if K is equal to positive R, and it's decreasing if K is equal to negative R. So what is K? In this problem, K is negative 0.2. So that means it is decreasing over time. That negative 0.2 tells us what the percent is, because according to this table here, I can find the percent by multiplying k by 100, okay? So that's what I'm going to do in this problem. I'm going to take my k value, and like honestly, the negative just means it's decreasing. And I'm going to multiply it by 100. And so I get negative 20%, okay? Or, just a 20% decay rate. And so that's how we can analyze an exponential function when it's base e. Base e means it's continuous. If the exponent is positive, it's growth, negative, it's decay, and then multiply the numerical part of the exponent by 100 to get the percent. Okay, so now let's take a look at how we use our compound interest in APY formulas when we're working with continuous functions. So in problem number 2, it says $5,000 is deposited into account. So that $5,000 is the principal. The nominal interest rate is 4%. We write that as a decimal, so R is equal to 0.04. How much is in the account 10 years later if the interest is compounded? Well, first of all, that 10 years, that's your time. And it wants us to calculate two different balances. One for monthly, which means N is 12. And so that means I would be using this formula here for N is 12. And then also wants us to find what the balance would be if we were compounding the interest continuously. So that means we're going to use the continuous compound interest formula, B equals P times E to the RT power. So I've already done these calculations for us. Check it out. In 2A, we were calculating the balance if the interest was compounded monthly, and so I came up with a balance of $7,454.16. In part B, when I calculated my balance, I got $7,459.12. So notice that when it's compounded continuously, I'm effectively making more money. That's because it's being compounded, that interest, at any given moment, as opposed to only 12 times a year, right? This E, by the way, is on your calculator. Takes two buttons to bring it up onto the calculator. So you should have a button on your calculator that is the second button, and another one that says natural log, LN. So if you press those two, it should bring up the E and a place for your exponent. Okay, so you'll have to try that out. So I mentioned that the continuous compound balance was more. It was effectively earning more. So that effective rate is known as your APY. And that's what they're asking us to find in number 3 is the effective annual rate. So the APY when you're given a continuous situation is equal to E to the R. And then from that, you're going to subtract 1. And then you're going to multiply by 100 to get the actual percent. Okay, so this $1,000 that's deposited doesn't matter in an APY problem. The 5% annual interest, well, the 5% is what you're going to plug in for the R. Just have to turn it into a decimal. So I did this calculation for us already. And this is what I plugged in to my calculator, and I got 5.127%. Okay, so this is how you analyze and calculate using base E. Okay, so we're talking base E functions are what I consider to be the continuous exponential functions. When you're working with base E and you're writing a function, you want to think about the numerical part of the exponent. It's going to be positive for growth and negative for decay. I'm going to turn that rate into a decimal. And then, of course, interest can be compounded continuously, and we can find our balance using this formula and our effective rate using this formula. And that's how Becker breaks it down.